Hello class. Today we'll finish chapter 6. The section is 6.6. We'll skip section 6.5, is not included in the curriculum. The topic is the frame and machines. Now previously we learned how to solve truss structures, and we said that a truss is composed of different members where every member has either a tension or compression. Now, the condition for a truss is that there's no load in between the joints. However, in the frame and machines, that assumption will be removed, and we will assume in certain circumstances and certain example that sometimes forces exist between two joints. Now, let's take some examples. The difference between the truss member and the frame member is that the truss member has no forces between the two end member joint, and the frame member, it does have some forces between the two end joint. Let's take some examples. This example involves a simple truss. So this is a simple truss. We have only a force applied at the joint B. The simple truss is composed of three members, truss members we call them, because at A we have reaction force in X and Y, and in the C we have only normal force on C, upward or downward, depends on the loading, and we have a load at the joint B. There is nothing in here between. As you can see, no reaction forces in between the members, and neither the external forces. So that's simple truss, and we use the previous method of section or method of joint to solve it. However, if you add an external force in between or between C and B or any other, such as external force P, then this becomes a frame member. Now, this frame member needs a little bit more work. What the difference in terms of the calculation is that in the simple truss system, the members or the truss members are undergoing either tension or compression. So we know their direction, we don't know their magnitude. However, in the frame members, the member that has force or reaction force in between will no longer have a known direction on the end joints, or the end joints will not have known direction. So let's explain that more details. We have here the same structure, truss member and frame members. The method of solution for the truss member follows the previous sections, where we draw the free body diagram of each member, and we know the direction in each one, assuming all of them has tension. So if you would use the method of joint, we label all the forces at joint B, and we apply summation of forces in X and summation of forces in Y equal to 0 at B, and that will guarantee us to calculate the unknown. However, in the frame member to the right, because the member BC does have an external load in between, therefore we don't know the direction of the forces at C and B, but what we know is the following. We know that the member AB still have either tension or compression because there is no forces in between. So therefore, when I draw the free body diagram, assuming it's a tension, I can label the direction as shown here. Now for the other side, BC, it is different story. The reaction force at C has unknown direction, but we can assume they have unknown components CY and CX. The load P still remains there, an external force and part of the calculation. We know that there is a reaction force coming from the joint B and it's that force is FB or FAB, but opposite to the one assumed for AB. So we label it here. It's going the opposite of that. In addition to labeling the external force F over here, we added to the member BC. So we have to add it either one, preferably, or we must add it to frame BC. So this way we can apply, for example, the equation of equilibrium, including the moments, to calculate these three unknowns, 1, 2, and 3. Now, frames and members are those structures or machinery that have at least one multi-force member in their structure. Example of the frame to the left, you can see that this structure has a member DB. There's no forces in between, therefore we know the direction of the tension or compression, but we don't know the magnitude. Member AB, however, or AC, has some forces coming from the reaction force at B. This structure tends not to change its configuration. It's just used to support external loads. As you can see, the motor is trying to pull an external force using this cable system, and so there is a tension on this cable that causes reaction force at B and reaction force at C. To solve this problem, we cannot no longer assume that beam AC is a truss member. It's a frame member and has multi-force. Similar example is a machine. This is a machine. As you can see, it can change its configuration, and so it has moving part. And this moving part, as an example, you can see that member HD has some external forces at F and C. However, I and H is a simple beam, is under compression or tension. Member CB is under compression or tension. Member BF is or BE compression or tension, as well as BE. But the member H and D is not. So that one has to be not assumed any directional forces of known direction. Looking at a frame structure like that one, the steps follows to identify the unknown, which are the reaction forces at A and C. Require, or B also requires the following. First step, always identify the two force members. In this case, it's AB. So AB, no forces in between, so we know their direction. Here it's assumed to be compression. Member BC, however, it's a frame member. So the direction of force at B, we know it's applied on that way, opposite of FAB. With general loading at C, CY, and CX. The number of unknown is 1, 2, and 3. So the simplest way to evaluate, for example, the unknown FAB by applying the moment at C for this free body diagram. So if we apply moment at C, immediately we'll be able to identify the force FAB. Now, if you want to calculate the SCX and CY, you apply the summation of forces in X and Y, and that will lead you to know the unknown. So this is, so what we want to be when we solve problem, we have to be very strategic in applying the equation, depending on what is required to be calculated. Sometimes the challenge is that you have several unknowns, and with practice you will know the best strategy to ease solving the problem. Let's take a look at this. Problem. It consists of a frame B, C. It's an L shape, and a link, a truss link, BA. Now the direction in the BA, because there's no forces in between, it's we know the direction of the force, so it's either tension or compression. Besides, always assume it's tension, and fix your coordinate system X and Y preferably x is to the right and y up, and both are positive in that direction. So to start with, the simple way is that we fix all the free body or the forces on each member. So since we assume here, for example, to undergo compression, let's say if it is compression, then we have a force that has a known direction and applied on the link BC or in the frame BC. So following these, the first step is fix all the forces on the link or in the L shape BC. The external forces are the moment stays and the force downward and FAB. It has no direction because it's again BA, it's a truss member. However, this link we don't know the directions of the forces at reaction C, so therefore we'll keep them general. Assume that this is the way it is. So to calculate the unknown FAB, you apply the moment at C. That will give you FAB. So the way you calculate the moment is simply assume the right-hand rule where counterclockwise is a positive. Calculate the moment at C. So you're gonna calculate the moment of 400 and add the free couple moment 800, and also calculate the moment of the FAB, which has an angle. Together, all of that will add up and equal to 0. So the solution is as follows. First, you're going to have two components or two moments generated for FAB. One due to the component in the horizontal, which is the component in that way. So you multiply FAB multiplied by the cosine angle, this angle, which is 3 over the hypotenuse. Hypotenuse is 9 plus 1 square root, so it's square root of 10, so it's 3 over 10. Multiplied by the distance. And now what's distance we are looking at? We are looking at the distance from here to here. That will cause a counterclockwise motion, which is the negative. Minus, so this is the first component, minus the other component of FAB, which is upward. So it is FAB sine theta or sine angle. Sine is 1 over square root of 10, and this is going to be in that direction upward. So what we expect this to do to the L-shaped beam is to rotate it counter or clockwise. Sorry, clockwise. So this is clockwise, so it's a negative. So both of them are negative, plus the free coupled 800 plus the moment of the 400, which is distance 2 multiplied by 400, and that's gonna give you equal to 0. We have one unknown, and that can be solved easily. So that's the method you should be following in the calculation, and hopefully, I'm narrating these steps. But it should be straightforward since we have done a lot of examples in the previous sections. Now to calculate the unknown reaction at C, use the free body diagram of the L shape, and that will lead to having one unknown, which we calculate the FAB and the CX and CY. So apply the moment, or apply, let's say the forces in X equal to 0, minus Cx minus the magnitude component of FAB in X, which is FAB multiplied by the cosine angle, equal to 0. So you're going to end up with reaction force. So it's to the right. Same thing for the Y. Let's revisit the first example we solved earlier and assume that there is additional change has happened to the structure, which is we add a couple moment at C. So assume that there is additional force or additional moment at C, right? So assume there is a moment. So does that change the approach, and how would you solve it? Now, because this free couple moment is applied at the joint, nothing has changed. So the only thing will happen is you add this moment to the equation to solve the problem. So if we scroll back to the problem that we solved here, I think we haven't solved it, but we mention it over here. So the same approach, when you apply the moment about C, you just add that free moment. So the answer for this problem is A. There is no change, right? There is no change. So that's the answer. However, if that force or moment is applied at AB in between, then definitely there will be some change, because AB no longer is a truss member, so we don't know the direction of the force. If that force is added here, so we don't know if this is compression or tension. What we know, we have two unknowns, reaction force at A and at B. So the answer is B. We'll have two forces, Bx and By at B. Now, the group problem solving example provided here is a frame structure. We discussed this structure before. It's not a mechanism, or it's not it's a machine. It's a frame structure, meaning it's used to support external loading. What is that loading? Is that, you know, coming from the hook, which is under weight 700 pounds. So the problem says here, giving that frame structure with the winch motor at W, we want to calculate the reaction forces at pin A, pin B, pin C, and also pin D. So as you know, the only frame structure we have here is A or AC. So this is a frame structure. The truss member is DE or DB, so we know its direction. So it's going to be pulling or tension. However, more forces will show up on AC. So we'll have here two unknowns, up and down, up and right, and B and C. So what's the method of solution? Now we're gonna do it multiple free body diagram. First, to calculate the forces, reaction forces at C and B. And once these are calculated, then we'll be able to calculate the reaction force at A. If you examine, and I will show the steps, if we examine the pin E, we know that this is under weight 700, and there is two tension here. So the tension, which are equal in magnitude, T and T, has to balance the 700. So 2T must be equal to 700. So T is equal to tension equal to 700 over 2. So if we know that force, then the next step is we want to calculate reaction force at the pulley C. So we draw the free body diagram of pulley C, which will have a force going down, and which is equal to tension 350, and another tension. We apply equilibrium equation in x and y, and that will calculate Cx and Cy. Similarly, for the pulley B, we draw the free body diagram. It has Bx and By. However, here we have two different orientation for the tension. One is going here, and the other is going with an angle. That angle is making 60 with the horizontal, or 30 with respect to AB. So we draw the free body diagram of that, and we calculate the X and By. So with that, we will be able to find the external loads applied on AC, where the loads on that beam or frame beam are the unknown AX and AY, the one we calculated at B, BX and BY, the one we calculated at C, CX and CY, in addition to the T, because this frame is connected to the cable So let's not forget that T also, which is 350. And also the unknown compression, which is, or tension, which is in that direction. So this way, we label all the forces on AAC, and we can calculate the moment, or we can calculate the force, unknown force at A by applying moment here, and also likewise we can apply moment here to calculate the unknown value here. So that's the strategy you should be following. Now let's examine the steps one by one and showing the quantitative analysis. So first we start with the poly E. Poly E, as we mentioned, under equilibrium, three-body diagram, and applying the forces or equilibrium equation. Summation of forces in Y is 2T, T plus T, minus 700 equal to 0, so T is 350. Now the second step is C. Now this is your C, poly C. Remember, C is under a tension, the same cable, from two sides. One is to the left and one to the downward. The way we determine that direction, imagine you create a cut. So if you're wondering how is that happening, is you just create a hypothetical cut here, and so the hypothetical cut will just cut all the forces on that pulley. Not to mistaken that beam here, I'm gonna change this one here. This doesn't belong to the pulley, it's in fact attached to the frame, so that's not included. So we have only a force here and a force here, which is, you see it labeled over here. So apply the forces in X, minus 350 or negative 350, plus Cx equal to 0. Cx is going to be 350 to the right. Similarly, forces in Y, Cy minus 350 equal to 0, so that Cy is 350. Now for the B over here, we isolate the B and you create this cut, right? And again, not to mistaken, these are not part of the pulley. Imagine that your pulley, you take it independent. So this will lead us to, because this tension or pulley always under tension, so when you cut it, it's gonna be equal in magnitude, opposite in direction, like that, right? To satisfy the tension in the cable, right? So this is 350 and 350 at an angle 30, and applying the forces in X and Y will lead you to the Bx and By as shown here. Okay. Now once this is all done, we know the reaction forces at these two pins, and now we label them on the frame AC. Now remember, frame AC consists of the following. We have the unknowns, AX and AY. We have the unknown TBD or FBD, name it whatever, at known angle. The reaction forces at B, and we have two things. In fact, we have a 350 from CX, and also we have CY 350, and we have also the T 350. So if you're wondering what is this coming from, and I need to explain this one here, this in fact is a CX, oh I'm sorry, it's a CY, right, plus the T, right, plus the both of them same direction, so it's a 350 plus 350, so it's 700. So this is like two added forces the same, so these are 700. Now what do we need to calculate? Assume I want to calculate the TBD. The easiest way is get the moment about A, cancel all this unknown, they will leave the equation of moment about A with one unknown TBD. So once you calculate, simply will become all the moments horizontal is 0, except those which are vertical. So we'll start with the TBD multiplied by sine 45, which is that component, by the distance 4. That's going to create counterclockwise, which is positive. Now minus this 303 pound force will create a clockwise orientation, so it's a negative multiplied by the distance 4, and also the 700 will create a clockwise rotation, which is 700 by the total weight from one end to another, which is 8. So 4 plus 4, 8, and that's equal to 0. One unknown in one equation, then you can solve and find the force. Now it's up to you if you want to apply the moment about B to calculate AY, but the easiest way it could be also by applying the summation of forces in X for the entire frame in equal to 0, and you have only one unknown, AX plus 175 minus 350 is going to give you equal to 0, and that's going to be one unknown, same as for the AY minus 303 minus 700 plus TBD, which we know the magnitude is 2409 multiplied by sine 45, right? That's going to be all equal to 0, so you can calculate the AY. So with this example, we conclude the problem solving. There is a couple of quizzes. I mean, it's an in-class quiz. It's nothing to grade, just to learn more about the strategies. Let's take this last attention quiz. When determining the reaction at joint A, B, and C, what is the minimum number of unknown in solving this problem? Now, first we need to draw the free body diagram. Now, drawing the free body diagram, this has so if I take member AB, you have one unknown FAB, tension or compression. So if I draw the free body diagram of member BC, so I have this FAB1, and this is not any longer a truss, it's a member, so I have 3 unknown. So 1, 2, and 3. So the answer is D. For the above problem, imagine that you have drawn a free body diagram of BC, which we did, right? And I must add these 2 known forces. So this is unknown, and this is unknown, and this is unknown, right? What is the easiest way to write the equation involving the B, or to find the unknown B? So what is the easiest way to calculate the force FAB, right? FAB, right? So if you apply the moment about C, these forces will cancel. You have only one equation with the unknown FAB. So therefore, the easiest way is to apply the moment about C. So the answer is A.